Greetings. This is a short video about manipulating series that you already know in order to create new series. Today you may remember in class that you derived the Maclaurin series for this function from scratch. So you took a whole bunch of derivatives and you set them all equal to the derivatives of an nth degree polynomial, and you found the coefficients. And then I said that that wasn't the most efficient thing you can do, because you might recognize this as being very close to the equation for a geometric series. Here. So I encouraged you to think about what type of substitution would you have to make here in order to, what sort of substitution would you have to make here in order to turn it into that function. And one thing we came up with was this. If I make a substitution and replace x with -1 minus x, that's the same thing as 2 plus x. And so I can make the same substitution into the series here, and I get the following. Let's take a look at this series very quickly in Desmos and see what it looks like. Well, before we do, why don't you take a minute and try and figure out what you think its interval of convergence probably should be. We know the original geometric series converges whenever absolute value x is less than 1. So with our substitution, that implies that absolute value -1 minus x should be less than 1. One way of thinking about this is it's like saying the distance between -1 and x should be less than 1. So if I think about where is -1, if the distance between my x value and -1 is smaller than 1, that takes me from 2 to 0. So that takes me in this interval. And here we are in Desmos. I've created a sum of p to the nth power, where p is -1 minus x. And we can explore what this looks like as a first degree, second degree, third degree, fourth degree, and so on. And indeed, just as we expected, it looks like between -2 and 0, this is matching the function 1 over 2 plus x fairly closely. One possible problem is that this isn't a Maclaurin series. And you can tell because it doesn't have the form of a Maclaurin series. A Maclaurin series would have a bunch of coefficients in front of powers of x. So is that really a problem? Maybe, maybe not. But if you'd been asked for a Maclaurin series and you just substituted this, that wouldn't be what was being asked for. So let's look at another way you could do the substitution. Starting with 1 over 2 plus x, if I factor out a 2 from both terms in the denominator, I get 2 times 1 plus x over 2. And you can verify that this makes sense because I could distribute back in and I'd get 2 plus x. Okay, so now that I've done that, I can remove this 1/2 to the outside, and I've got 1 over 1 plus x over 2. Okay, so this is actually much closer in form to the geometric series that I want it to be. So I can again keep the 1/2 here, and I can rewrite this as 1 minus something. And that's what the substitution would be. But in this case, it's just -x over 2. So as you can see, I can write my original geometric series only I'm multiplying my entire geometric series by 1/2. And then I'm making a substitution where instead of each x, I have -x over 2. This may not look obviously like a Maclaurin series either, but this is something that we can simplify. So here, if I actually raise each of these to the appropriate power, you see we end up getting an alternating series because all of the even terms end up being positive and all of the odd terms end up being negative. This is a totally different series, you'll notice, than the series that we got up here. Let's take a look at what this one looks like inside Desmos. So here we are in Desmos. I have 1/2 times the summation of -1 to the n over 2 to the n times x to the n. So I've got a linear approximation, quadratic, cubic, 4th degree, 5th degree, 6th degree. And as you can see, this is also matching the function, only this time it's pretty clearly centered at 0, which is what you'd expect for a Maclaurin series. So here we've actually successfully produced a Maclaurin series, whereas before we'd produced kind of a weird Taylor series centered at x equals -1. So what's my point? I have 2 points. First is that there's always multiple approaches you can take to a problem. My second point is, even though you can produce a series, pay attention because different series are different. And a Maclaurin series is not the same thing as a Taylor series because they're centered at different locations. Last example is a short one. If I asked you to find a Maclaurin series for this, again, you could just go ahead and start taking derivatives, or you could start with the series for sine and multiply it by x. So term by term, I've just multiplied each term by x. So when you're working with series, remember that you know several series already. You know the series for 1 over 1 minus x, for e to the x, for sine, for cosine. But those are all only Maclaurin series. You can multiply your series by something. You can divide your series by something. You could integrate your series term by term. You could differentiate your series term by term. Or you could perform a substitution. So there's a lot of choices to work with. And that's some of what you're going to be practicing in class on Wednesday. However, if I asked you to find a Taylor series for sine x at x equals pi over 3, you can't start with the Maclaurin series. Because the Maclaurin series, the coefficients are built so that the series will be centered at 0. And if you want to center it somewhere else, you have to go through the whole process to derive the coefficients for yourself. Okay, so check out the next video, and that will be the last video for your homework.